Hello everyone, I hope you're doing well. In this video, we'll be talking about functionals and functional derivatives. Functionals are incredibly important in physics. If you want to understand that how nature behaves fundamentally, then understanding functionals is crucial. We have seen functions since ages. We know how to define them, how they look like, and how to differentiate them, how to integrate them. For example, we have a mapping from a variable called x, the independent variable, we know that, and we map it to y variable. So a point x1, for example, defines a corresponding point for y1, x2, y2, and we can form all of the ordered pairs, and each x point uniquely defines a y point, and we know about functions that they are unique ordered pairs. Okay, so we have point-to-point dependence between the two variables. The y depends point-wise on x. A particular x point defines a particular y point. Alright, so these are some mathematical restrictions that we give for any relation to be a function. Not all the relations are functions, so this is just to be specific. However, we know that inserting a number x gives a number y, so it's a mapping from a number field x to a number field y. So it's from number field to a number field. However, in case of functionals, the case is a bit different, and we'll see how. Okay, so having a concept of functions in mind will help us to form an intuitive understanding about functionals as well. All right, and keep in mind that it's a mapping from a number field to a number field. For example, if there is a function y is equals to x squared, so how do you find the graph of this function? For example, you'll put the value of x and you'll get corresponding value of y. You'll put x is equals to 0, you get y is equals to 0, x is equals to 1, y 1, and you get a graph like that. Okay, for all values of x, continuous values of x, which is real numbers, which could be complex number, whatever, it could be a real number or complex number. If it's a number field, it could be any number, and you get a corresponding relation. Okay, so you put a number and you get a number. That is how the functions behave. All right, so keep that in mind. It will help us to see how functional behaves in contrast. And most importantly, we'll also understand that how to find out the functional derivatives. Functional derivatives is where the application of this concept lies. We'll see that, and we have seen the derivation of functions. However, here the derivation is a bit different and it's a bit low level. It means that you have to deal with definitions, but they are not as much difficult. Once you understand the underlying concept, it's super easy to find it. I'll give you a super easy method to calculate functional derivatives, and it works every time. All right, so we'll solve multiple examples, all kind of examples, and I'm pretty sure that after these videos you'll be expert in finding out functional derivatives. All right, I told you that they are incredibly important in physics, but you might be asking in your head that Amna, we haven't heard about functionals as often as you are stressing that they are important. So the reason is that normally what we study is the surface level physics. Okay, we study the major concepts, the surface concepts, but if you are doing specialization or PhD, that's where you encounter the deeper level physics, where you get deeper categorization, and you see that the concept that you used to think that they are not as much important, when you have deeper studies, you come to know that they were incredibly important, and that's how you find functionals important as well. You'll see them as really important in classical field theory, in quantum field theory, And in mechanics in general as well, you have seen the Lagrangian equation of motion, and if you understand functionals and functional derivatives, you will see that there is one special function that is called as functional that is called as action. Action is a functional, Lagrangian is a function. Okay, we will see that as well. Action is a functional, and the stationary nature of action, this concept leads us to Lagrangian equation of motion, and the derivation involves the functional derivative of action. So that's also an instance on finding out the functional derivative. We will solve it later. However, I'm giving you an overview about functionals, how they are important and where you'll find them helpful. This was the quick context about functionals. Let's quickly get started with this video and try to form a good understanding about functionals and functional derivatives. Alright, so let's first introduce ourselves to functionals. In function, we saw that function takes a number x as argument. Okay, argument means what you put as input. So here input is x, which is a number. However, in functionals, a functional takes a function as argument. Okay, so in case of functions, we use round brackets to show the argument of it. However, to make distinction from functions, in functionals, we use square brackets to show the argument of functional. So a functional takes a function as its argument. Okay, and in loose words, we can say that a functional is a function of function. Okay, so it takes a continuously valued function as its argument, and don't assume that this function f is defined at a single point x and it's taking it as an input. No, it's taking the whole curve, the complete curve as input. Okay, it's not taking a single value, in contrast to functions where to find out a value for example y, a particular y value, we put a particular x1 value, a single value we put in and we get a single value for y. However, here we put the all possible values of this function as input to this functional to get a single value for that functional. Alright, so this functional takes a function as input and gives a single number as output. That is the major difference. Alright, so I hope you see the difference, and let me write down this thing again so that we can make a distinction really clear. So it is like that. We represent functionals in this notation, in which we have that capital F, sometimes they use gamma like that. Okay, and square bracket starts and you write down the argument in which this functional depends. If it depends only on f of x, you just write f of x. Okay, like that. And you can also reduce it in this form. For example, we can omit this thing and we can make it, obvious that it depends upon, for example, some space variable. So we can just write it like that. It's also fine, or you can make it f, that's fine as well. And in other notations, if we have multiple dependencies, then what we can do is that we can have dependencies. For example, if we have for example f, and for example it depends upon two different things, and it could be, for example, x, it depends on x, and it depends upon f of x. You can write it like that, and you can also write it like that. For example, the circular brackets and then x and then square brackets. In square brackets we have that function and this closes. Okay, you can have this notation in that way as well. and so on. For example, if we have dependency of functional into two different, it happens that it depends upon, for example, phi of x and phi prime of x. Whenever there is a function inside, you always put square brackets. Okay, and if we have that space variable inside it, there's two options. You can use this notation or this notation. Both of them are perfectly fine. All right, so yeah, these are different kinds of notations that you can adopt for representing functional. They're all equivalent, and I hope the notation is clear here. And also I really hope that you got the clear idea about the input of functionals, which is a continuously valued function, and this f of x is the whole curve. Okay, it's the whole curve, it's all of it, not a single point. It's not defined at single point. For example, like you take this point of x and its y, and you are calculating the functional at a particular value of f of x. No, that's not happening. You are taking the whole trajectory as input for this functional, and that makes it different from functions. In functions, we take only a single value of x as input and we get a single output. However, here we take all values of f of x at all values of x as input, and we get a single number as output. And that's the beauty of functionals. It takes as argument the function, the whole trajectory. Okay, keep that in mind, and it gives out a number. So it's a mapping from a function space. It's a function space. Okay, it takes input in function space and it maps it into a number field. Okay, it's a mapping from a function space to a number space. Okay, and this number could be a complex number or a real number. This is the difference between the functions and the functionals. And yeah, this is all about what in introduction you should see about functionals. It's a mapping from f of x as argument to a functional. Okay, or you can write it simply like that. That's totally fine. All right, and for functions, you saw that it was a mapping from x to f of x, and it's single valued, but here you take the whole function and this whole trajectory, all possible values are input to that functional. We'll see that how it looks like. Okay, you'll get a better understanding of it when we'll be doing the examples. However, for the initial understanding, I hope that is enough. And okay, so this is the initial introduction to functionals, and I hope that you understood the difference between them. And now let's see that how we define its derivative, and comparison with the derivatives that we defined for functions helps us to make a good comparison, that how they differ from each other, because we understand derivatives of functions really well. So comparisons really helps us to see where we are heading towards. So all right, so for a function which is, for example, f of x, we know we define its derivative as with respect to, for example, x, or maybe y. We can take y not and we see its definition as limit delta y approaches to 0. Delta y, if the derivative with respect to dy, then it will be delta y. If its derivative with respect to x, then it will be delta x, and so on. Depends upon which kind of variation you are looking to. So if it is in y, so it will be delta y approaches to 0, and that will be equals to, there is the function when we have this variation in it. For example, x plus delta y, we change the argument of function by a small change delta y minus the original function divided by the change. Okay, this is how we define the derivative for functions. Now let's see how we define the derivative of functionals. If we have a functional capital F, so we know that it depends upon a function f. So let us see that we will define its variation, that f changes into f plus e, which is a small change, times some phi field. Okay, so we can express it equivalently in that form. Here you can say that this is a small change in field that we are adding in that field. Okay, so here you can assume that this is a small change in field that we are adding. We are just expressing it in terms of E, which is a small change. Okay, so it's the parameter of perturbation, that how much perturbation we are adding in it. Perturbation is actually this small change that we are making to it. So the expansion in terms of E leads us to this form with some assumptions in mind, but that detail doesn't matter. So we can proceed with this situation. Okay, so we see that we are changing this field to this new value, which is f plus e phi. So we can write down its derivative like that. Alright, so we can see the scenario in here, and similar to what we have written for the derivative of functions, we can write the derivative, functional derivative of functional. Okay, and we use it in that way, like we use this symbol, this type of symbol, to write down the functional derivative. And it is, for example, with respect to phi. Okay, it's always with respect to some field. It could be phi, it could be g, it could be f, it could be anything, it depends. However, we are just here writing down the general expression. So that is equals to limit e approaches to 0, because here the perturbation is expressed in terms of e. Previously it was in terms of delta y, so here it's in terms of e. So e approaches to 0, and the value of functional at this perturbed situation, which is e plus phi, minus the original one divided by e. So this is the definition of functional derivative. Okay, using this definition you can also find out the functional derivative of any functional. However, there is one more simpler method to find out the functional derivative, and I'll be using that one method a lot because it's more easier to deal with, and I will be using that one. So let's see that relation. Well, as we have seen the basic definition of functional derivative, now let me tell you some of the relations and properties that are helpful in calculation perspective. Okay, these are some properties that these functional derivatives follow, and also some other helpful forms that helps us in calculation of functional derivatives. So these are the forms that I'll be using throughout, so keep that in mind, and they are really important forms. So first is the variation in functional. Variation in functional is represented by this variation symbol, and since it's variation in functional, so it's this variation in functional capital F, and we can write it as a function of, for example, f. Alright, so that is equals to, now this variation in functional can be expressed in terms of two forms. One is integral form and the other is differential form. Both of them are equally important. Alright, so let's write down the integral form first, which is integral of functional derivative of f. Okay, and if it's f of x, the argument is f of x, and it's defined at x with respect to f of x prime. Okay, here you can see that f of x prime, this is field, this is not functional. We are finding out the functional derivative of functional with respect to our field. Okay, so and then we have a test field here and dx prime. Okay, keep that in mind. Here the argument is in x, here it is in x prime, and that matters. Alright, so this is engraved in its definition, so it matters what it is in it. So yeah, and since the integration is on prime variable, so here in argument you have x, not x prime. Okay, here it's, if I for example write down the argument that will be here, so it will be x, because you can see the integration is done on x prime, so x prime will vanish. So here you have argument on x left behind. Alright, so yeah, this is one of the form, this is the differential form, and now let's write it into it's an integral form, and let's write down its differential form, that is equals to d by de, since it's variation. So variation with respect to e, because e is the perturbation parameter of functional, which is the new one, the perturbed one, and it's f plus e phi. Alright, and you must have guessed it right, since we have used here the prime variables. Here we'll have prime variables as well, so it's d by de, and at e equals 0. Okay, since we are defining a variation, so e at, it's defined at e equals 0. At the end, after solving everything, you put e equals to 0, so you know, to make it mathematically feasible. So here it's what I was gonna do. Yeah, we were about to write down the dependencies, so it's f of x prime plus e phi of x prime at e equals 0, and I'm defining these things so that we can make a comparison between these two, and you will see that why it's important. Even if you take from using x, you can, you know, relabel it afterwards. It's just a dummy representation. That doesn't matter if you take x prime, x naught, x, or whatever. Just to make you understand it better and picture it better, I just make this comparison that it's x prime, since we take here, because at the end you will see that we can express this form. We will start from this form. Okay, at the end we'll get this form, so that we have this as one term, and the coefficient of this is the functional derivative actually. So it's the coefficient of phi of x prime. That's why I said that start with x prime representation, so that it's easier for you to picture the result and compare it with this integral form, and this comparison will help you to find out the functional derivative indirectly. Okay, and this is really easier to do, that is why I'm using it. So this part is actually the functional derivative. Okay, and this is just a variation of functional. Keep that distinction in mind. This is the variation, it's just like delta x or delta f or delta y. It's like that, it's just variation. This is the functional derivative. Okay, and we use this formula, this and this formula in combination to find out the functional derivatives. So yeah, I hope that you get it, and let's write down some important properties of functional derivatives that will help us in computation of functional derivatives. So the first one is that if we are finding out the functional derivative of some function f of x, its function, because you'll have that form later on, you'll see when and how. So if it is being calculated at two different points, one is x and another is x prime, so it will be equals to the direct delta function of x minus x prime. Alright, so you can see here that this is the Dirac delta function. Alright, and you will see that multiple times. Next, another form is that, for example, if we have a function f of x, this is function, not functional. Keep that in mind. And functionals are always represented by capital letters. For example, capital F, capital G, gamma, or something like that. And functions are represented by small letters, which are small f, g, h, like that. Okay, so that distinction helps, you know, to have distinction between functions and functionals. So if you are finding out the functional derivative of, for example, f of x with respect to g of x, and they are independent functions, so it will be equals to 0. Okay, so since f of x and g of x are independent functions, so they will vanish. And other relation is the linearity. For example, if you are finding out the functional derivative with respect to some phi field or f field, whatever, and if we have a and a functional of, for example, f plus b and a functional of g, for example, and you can distribute it. Okay, you can write it, a is a scalar quantity, so it will come out times the functional derivative of the first thing, and then b, it's a scalar quantity, so it will come out of and functional of g. Okay, and here you just don't need to put, since it's a functional, okay, it's a functional of g, it's not function, you will not apply this thing here. You will say that, oh, okay, it's a functional of g, so I'm just directly putting it equals to 0. No, that's not how you will work. Okay, so we'll see how this works, but this is the just general representation, that if you have two functionals and you are applying a derivative, functional derivative on them, so you can distribute them among them. Okay, it's like linearity exists, so you can write separately on this and apply it on this. Okay, this is just a really trivial identity that normal derivatives also has, and you know that. So yeah, these properties will help you to make sense of it, and we have seen quite a bit important relations. This is the general definition. You can also find out the functional derivatives using this general definition. However, this method where I have shown you people the integral expression of a variation of f, okay, which contains the functional derivative, this is a functional derivative. Okay, and we saw that this variation is also equals to this differential form, and we'll see that using this differential form we can write it in this form, and we can extract functional derivative out of it, and it's incredibly simple. So in next video we'll see the application of these formulas, and we'll find out the functional derivative, and it will be super easy, I assure you. Okay, so till then, take care, and if you have any questions you can ask me in comment section. It's been a while that I have talked to you people, and I'm really happy that I'm back to that schedule of uploading videos for you all. So yeah, take care and goodbye.